maybe not. We can access that.
Will you? Okay, I guess we can start. Good morning, everyone. Welcome to the panel discussion on deep UV innovation, shaping the future of photonics. My name is Michael Kneißl. I'm with TU Berlin, and I would like to introduce our panel first. Asa Hacklund from Chalmers University of Technology in Sweden. Welcome, Asa.
Thank you.
Then we have Tanja Mehlstäubler from PDB in Braunschweig. And we have Martina Meinke from the Charité in Berlin here. Thank you to our panel. Let's welcome our panel. So you might be wondering what it means, deep UV innovation. So we will be exploring how innovation in UV materials and devices, particularly semiconductor UV LEDs and UV lasers, is transferring and impacting real-world applications and from atomic clocks to in vivo disinfection. And the panel discussion is in two parts. In the first 15-20 minutes, we'll have perspective from each of these panelists on various UV applications and UV sources, and then we'll open up for discussions and hopefully a lively number of questions from the audience. Before we do that, in case UV doesn't say anything to you, I'll have a short primer on what is actually UV. And you're probably very familiar with the colors of the rainbow, starting with the red, going to the green and blue spectrum. And if you go at shorter wavelengths, below 400 nanometers, you enter the ultraviolet spectral range. That goes between 400 nanometers and 100 nanometers. And this range is divided up in some subsections, UVA, UVB, UVC, vacuum UV, depending on how this UV light interacts with biological systems. The main message or the main takeaway is UV photons have a high energy, energies that are high enough to break chemical bonds. And then you can use those UV photons, for example, to fight bacteria and viruses. You can also use these UV photons to excite atoms and ions for atomic clocks, for example. The question is, what kind of UV sources do we have? If you look in nature, of course, the sun is our major source for natural UV light. About 5% of the solar irradiance is translated in UV light. But because of our atmosphere, most of this UV light is filtered out. So UV light reaching the surface is 280 nanometers and longer. And there's another technology, the mercury vapor lamps, that provide UV light in the 254 nanometer spectral range mostly, which is well established, widely used, in particular in water disinfection in your utilities. However, as the name already indicates, mercury is a toxic chemical, and these lamps are gradually being phased out due to Minamata Convention and UV Rose Directive. And what we are talking about today is semiconductor-based UV LEDs and lasers as a very efficient and environmentally friendly light source. And just to give you some numbers, UVC LEDs are already with wall plug efficiencies at 10% commercially available, and these numbers are steadily rising. And more recently, we have seen the first demonstration of UVC and UVB lasers. And so these devices will not only replace conventional technology, they will enable new applications. And I've listed a number of these applications here in this slide, starting with metrology and atomic clocks, medical diagnostics, phototherapy, biochemical sensing, 3D printing, UV curing, water treatment, clean air, food safety, in vivo disinfection. And we're just picking two of those applications today. Otherwise, we wouldn't have enough time to illustrate the potential of deep UV innovation. And with that said, I would like to introduce our panel and give them a chance to introduce their view, their perspective on this topic, starting with Asa Hacklund on deep UV sources. please.
Thank you very much. So I'd like to talk a little bit about the deep UV sources that we have available and what will come next. So as Michelle said, we have both LEDs today and also the first lasers being demonstrated. Both these type of light sources are interesting for applications because they have different properties that can be explored. This comes back to the physics in the devices. So an LED is based upon a spontaneous emission. So you excite the material and then it de-excites itself and send out a photon. Now this photon can be emitted in any direction. It's a spontaneous process. So an LED would emit light in all directions, more or less. Then you can have transitions for many different energy levels. So you can have a broad spectral range of that LED. So it emits different colors, you can say. And because it's emitting slightly different colors and it also goes in all directions, the light is very unpredictable or incoherent, as we say. But these are properties that are very good if you want to use an application where you need to illuminate something. So, for example, disinfection in phototherapy and for UV curing, LEDs are very good. Then lasers are based on a different physical process, so that's a stimulated emission. So you have an incoming photon that will stimulate this transition to take place, and now the photon that you generate is an exact replica of the one you had. So it's basically a photomultiplying process that occurs. So now that means that your emitted photon now has the same direction, so you get a well-defined beam coming out. It also has the same wavelength, so you get a very narrow spectrum coming out from that laser. And it is also in phase, so they are both going up and down in the same position in time. So you basically generate a super wave coming out from the laser. And this gives the light a very high predictability, so a coherence in light. And these are properties that can be explored in lithography, 3D printing, atomic clocks, spectroscopy, interferometric measurements, as well as in communication, because you can also modulate, turn the laser on and off very fast. So there's a need for both type of light sources. Now, when it comes to LEDs, as Michelle said, we have good performing LEDs as it is now in the UVC. And they are competing with the mercury lamps. And there they offer a number of advantages, such as you can get a UVC LED at basically any wavelength you want in the UVC. You can also make LEDs in UVB or in the UVA, so you have a broad spectral range which you can cover. They're also environmentally friendly because they don't contain mercury. And they also have very long lifetime now, so they're very interesting for a lot of applications. And the wall plug efficiency is continuously increasing. So they will outperform mercury-based lamps potentially eventually. When it comes to UV lasers, on the other hand, there are commercially available only solid-state lasers that are frequency quadrupled, or excimer lasers in the deep UV. And these devices are kind of shoebox-sized devices. They are very low power efficiency, and in addition to that, they're also very costly. So if we could make semiconductor lasers instead at these short wavelengths, it means that we will have a very compact light source in the grain of a sand, basically in size. It can have very high wall plug efficiencies potentially and would cost maybe €1 or 2. So there's many applications that would benefit from having semiconductor lasers. So you can imagine developing many different types. There are edge-emitting lasers, there are surface-emitting lasers, both of a VCSEL or a pixel type. The edge-emitting laser diode is the ones that is easiest to make first, and they can provide very high output powers potentially. This has been demonstrated for blue devices, for example, but they do suffer a bit from the output beam being very divergent and not circular symmetric, which makes it difficult to couple that light into the application that you want to use it in. Then you have the surface emitting laser like the VCSEL. This is a very small device, so it will not emit the same amount of output power, so maybe milliwatts instead of watts, but it does have a very nice circular beam coming out that can be quite low divergent. Then you have the photonic crystal-based surface emitting laser, that a bit more newer type of semiconductor laser. They can, as the edge emitting lasers, develop or produce very high output powers, so in the watt range, and do so with a very nice beam profile. So you will have a very super low divergent beam coming out that has a divergence of less than 1 degree, so really a very nice laser beam. When it comes to the deep UV, what we have seen today are electrically driven edge-emitting laser diodes recently been demonstrated, both in the UVC and just a few months ago in the UVB as well. When it comes to the surface-emitting devices, there are no electrically driven devices yet, but we have seen the first demonstrations of optically pumped deep UV VCSELs and pixels. So why is it not so easy to make these devices, you may ask? One is that to make a laser, you need to have a really high optical quality resonator for the light to resonate in, so you can achieve lasing eventually. You also need, because you want to drive current to your device and convert that into optical output power, so you need to have materials that are electrically conductive. And for those of you who know a little bit about semiconductor physics, it means you need both high N and P-type conductivity. And this is not easy to achieve in the aluminum, gallium nitride materials that we need to use to have high enough energy levels so that we get emission of UV photons. But the great promise is that there's been a lot of improvements in the last years. So we have seen a huge improvement in material quality and also in the type of mirrors you can incorporate in the devices, which has really enabled the demonstrations of the edge-emitting laser diodes that now are continuously operated. We also have found new ways to make electrical conductive materials using built-in electric fields in the materials. And we just, I think maybe a few months or a year ago, saw drastic improvement in electrical injection efficiency. So the current you inject, that the carriers go to the right place and emit photons, basically. And so I would say in summary maybe that I think we are on a very good path towards electrically driven semiconductor-based deep UV lasers. And for a brighter future, I would say. But the question is now, what can they be used for? So I guess I will hand over to you guys.
Thank you. So yes, hello, good morning from my side. My name is Tanja Milstäubler and I'm from PTB. So that's the logo in the center. That's the German National Metrology Institute in Berlin and Brunswick. And I come from a few of applications, and I'm really excited to see from also what have been the big achievements already in the past year, the big progress to give us better and better UV sources in terms of higher power, a better mode quality, because that's important for us to then guide the light, to bring them to the atoms, to the ions, and use them, in our case, for quantum applications. Who are the candidates who need UV light? They're mainly ions. So if you take off an electron from an atom, you shift all the resonances into the deep blue and even ultraviolet. And that's the big challenge as soon as you do ion-based quantum technologies. These quantum technologies may be used for quantum sensing, building atomic clocks, or even quantum computing. I would claim quantum computing is the largest field for laser-trapped and cooled ions, and this is the field where we need deep UV sources. I put here a few of the example wavelengths of different atomic candidates: calcium, ytterbium ions, beryllium ions, indium ions. These are all hot candidates for quantum computation and atomic clocks. And you see the wavelengths are shifting more and more in the ultraviolet and deeper violet. So this is challenging for us, how to deliver reliable light sources and how to do the light conditioning and distribution. You see here also some photos from our CCD camera of actual trapped ions fluorescing in the ultraviolet light. We collaborate also with Infineon, that's why the Infineon logo is there, in order to build scalable ion traps for quantum computing and for sensing. So we do both develop ion traps in our cleanroom center at PTB, but then of course if you want to go in mass production and do it in a professional way, you want to collaborate with big industry partners and bring them on a CMOS process. But there we have to think now how we can incorporate and integrate nanophotonics that is suitable for blue and violet light. This is a huge challenge in the future. And yeah, the vision, as I said, is on one side the quantum computing, and this is just a rough scheme how such a quantum CCD processor will look in the future, where you can shuttle hundreds of ions in crossings, you do quantum state manipulation gates, you move them over into a reservoir, you see some lasers coming out from the ion trap for quantum state detection, even if the qubit manipulation is done probably with a microwave, but then for the readout, for the cooling, you will always need optical lasers speaking to the ions. And now you can imagine if you want to build a competitive quantum computer, you don't want to have 100 qubits, you want to have millions of qubits. And the only way to scale up to millions of qubits, you have to integrate the photonics on the chip. That's the big challenge. The same holds for atomic clocks. You see that on the right side. That's the vision of atomic clocks on a PIC, on a handheld atomic clock for relativistic geodesy, to bring them out in the field, to measure height potentials, to bring them in space for global navigation, or even for future quantum communication and telecommunication. 6G and beyond will be based on optical frequency standards. And this is another scheme from a beautiful paper that was published 2 years ago that gives a very nice roadmap of all the challenges that need to be accessed and to be done in order to bring all these many parts that we have in our laboratories nowadays in free space, to manipulate the laser light in a passive way, to distribute it, but also to condition it actively with acousto-optic modulator, electro-optic modulators, switches. These are all photonic parts that need to be developed for the UV. Yeah, and this is how it looks like in the very first beginning. So we already do have actually integrated ion traps with UV and blue photonics on board. And this is actual measurements. The color code is to make the UV and infrared and everything visible. But this is actually already a produced ion trap at 20 in the fab, where light, even down to 370 nanometer, is guided to the ions and hits, basically everything meets in one location where the atoms, the ions, are trapped. And at PTB, we optically characterize these and go in iterative steps with the fabrication people. And we see there's a long way to go. I'm happy to discuss that now. But we already see also very encouraging results in terms of low losses and great guidance. Yeah, this is now from the quantum perspective. And I hand over now to Martina, who will give us the view on the biologist and medicine perspective.
Yeah, thank you very much. Welcome to my pitch here. I'm from the dermatology, so department. I'm a medical physicist. And I think if I will tell you, do you want to have UV on your skin? Usually the reaction is no, and even worse in the dermatology. They would say it's avoided, it will damage your skin, you will have DNA damage. So why could help us far UVC in medical health? And I want to take you on a journey. We have two problems at the moment. One is the antimicrobial resistance, AMR. And you might know that we have a lot of deaths due to this problem, 10,000 in Germany alone per year. And it will increase, and worldwide it's more than 1.2 million, and it will even increase. And this is only counting which directly are caused by AMR. If you look associated with AMR, we have 5 million and even more. And one very famous one is the MRSA. But it's not restricted to us. There are new popping up, and if you develop new antibiotics or antiseptics, usually they could turn also to become resistant, so the bacteria become resistant. And therefore, we need something new, maybe thinking in a different way. And the second problem is the pandemic. You all know, still in our mind, I think. And it will maybe come a new one. We have SARS, we have COVID-19. And also there we have 7 million now deaths to 2024. So I think there we need something where we could lower the distribution. We will not, of course, immediately take it away, but the question here is, could light help us, and UV light? And if yes, why? And you all know 254 is mentioned, it's good for disinfection, but it's hazardous. That is therefore the people said, if you go even deeper to far UVC with more energy, are you crazy, Martina? That was usually even to physicists, why should this help us? And here we said, okay, let us think damage can only occur where it goes. yeah, where it reaches. And if there is no light, why should there be any damage? And this is maybe the trick. If you look on the right side on the image, you have UVB, you have UVA, you have normal UVC, and it goes to the viable cells. To the viable epidermis, we have here the upper layer is the stratum corneum, and this is their death cells, no nucleus, so you can't induce any damage there. It's absolutely no danger there. And if you look to the arrows at the far UVC, we have two wavelengths here, 222, that's an excimer lamp, and the 233 nanometer, which is a new LED produced in the Technical University, the FPH. And here we can see it's more or less completely absorbed in the upper layer. And this is why I told you, if it doesn't come down to the viable cells, why should it make any damage? But on the other side, on the surface, where you have your microbes, your MRSA, or whatever, you can kill them. They are only 1 micron, and you reach the DNA there and damage it. And that's very important to keep this in mind. But nevertheless, we have to prove this. That was the hypothesis. And we have to look to the skin, of course, because if you want to make antiseptics on the skin, where you have the microbes, or maybe in the mucosa, in the nasal cavity, where the microbes hiding and waiting, okay, now I can come out again, where they want to destroy them, and light guided by fibers would be very nice to reach this. It's not easy to kill them there. You can look sprays or something, but they don't work efficiently. And the eye, of course, is critical. But the eye, we have always keep in mind, you can wear any glasses, and then there is no risk anymore. Okay. We had to solve or to find one dose where you have this optimal biocidal effect, and on the other side, no damage to the tissue. That was the aim in the past. And we can look first to the germs. Viruses are very small, nanometer scale. They are easy to kill. It's a little bit depending where you look on them in the cell alone, but you need only 20 millijoule per square centimeter, and then they are killed. If you go to bacterials, which are around 1 micron, we also could be shown that not only for the MRSA, but for a lot of others, you can kill them more or less with 20 to 40, and even maybe a little bit higher, 60 millijoule per square centimeters, you can kill them. So that is no problem. And the 10-fold bigger fungi, which is not, there are even more problems because we don't have so many pharmaceuticals to kill them. They also get killed at least with 60 millijoule per square centimeter. So this is the absolute maximum what we need. And now the question, is it safe to the tissue? And we did a lot of investigations. We did ex vivo, in vitro, and for the skin also in vivo investigations on volunteers, different age, different skin color. And what we could conclude, an example from the skin, that if you go out 10 minutes into the sun, I think you can't avoid this, and it's healthy. You need some vitamin D, and even for the dermatologist, it's acceptable, yeah, so we fight it for this. Our damage is quite far below this if you look to the skin. If you look to the mucosa and the eye, it's comparable because you have mucin on, which absorbed already a little bit, and for the eye you have tears, and you usually don't expose directly to the light. So here we could conclude for the germicidal dose, it's safe for all tissues. So therefore, we are quite happy to conclude we are able with far UVC to kill the germ and spare the tissue. And the idea is now, where can we use this? I think it should be a controlled situation because here we can control the dose. So for medical application, it would be wonderful to have it. Just 2 examples here. Getting rid of the MRSR or the germs in the cavity, light, also using lasers, it would be great for this. With the LED, we could use for wound healing. If you have chronic wounds, we have multi-resistant germs in, and of course room disinfections. You also can do pre-antiseptics to avoid surgical site or reduce surgical site infections. And if we have a pandemic situation, we also can irradiate public areas. That is an idea because you always, under controlled condition, you always have to judge the risk and benefit for the people, for you, for all of us. Thank you.
Thank you very much. I'd like to thank all the 3 panelists for their perspective. And now we're open for questions from the audience. So let me see whether I see any hand. Maybe you have to first digest a little bit the information you received. Maybe I start with the first question. So in terms of maybe Martina, what would you think does it take now from a lab environment to bring this 5VC disinfection into real-world applications into hospitals? It seems like it's a very important thing to do.
Yeah, that's quite a big step where we're standing now. First, we have to get rid of the fear. The fear, if the people usually hear, that is where I started like this, we want to irradiate people or rooms where people are present, or whatever, directly use it for antiseptics, it's hard. So I think if you have a big problem, if you have a multi-resistant germ, if you have a chronic wound, or if you go into the hospital and want to get rid of your multi-resistant germ, there you have a need. So I would start in the medical field directly. Therefore, we need companies producing a medical product. This is European regulation now. We have the MDR, the medical, that we have to think about. It's of course it's breaking down, or it's broken down to the German law as well. But here we need companies which say yes, let us do this step. It's not easy. It's highly regulated, but I think that is the starting point.
Thank you. Yeah. Question.
I have
Yeah.
a question related to laser.
Can you wait for the mic? So just perfect.
I have a question. Is it on? Yes.
Yeah.
So I have a question for the relation between the laser technologies and the medical applications. So in your talk, I have not understood what would be the differentiating point of laser technologies in order to generate those light sources. So are there specific applications where laser technologies make certain sense?
Yeah, I think if you want to go on the cavity, you need a fiber-guided system that would be good with a laser. And also, all the, I could not go in all details, but at the moment the LED is filtered, the excimer lamps are filtered to avoid the higher wavelengths. And this is of course not necessary for the lasers, and they have enough energy, they have enough intensity, and to kill the germs inside. I think that would be wonderful. In contrast, we could use LEDs, but there we have to filter them, it's bigger, we have partly to cool them. So a laser, and especially if it's a small one, would be great. The idea is really, if people come having a germ putting in a stick, you all know from the corona as a test little tool, and this could be then done with a laser-guided fiber or something like this. Fiber-guided laser, yeah.
Thank you. So the next question was over there. Yeah, please.
Yes. One of the biggest problems is from the material science perspective, that it's really hard to make far UVC LEDs and diodes solid state. Do you see that as being the key for widespread implementation, is cost reduction via solid state sources like LEDs and diodes that are grown at wafer scale?
Maybe Asa, if you want to answer, or
Yeah, I mean, I can start and you can fill in. So,
okay.
I mean, Michel is really a material expert, so he would have the strongest say in this. But there's, I would say, to make these devices better, you need both material scientists that can improve the quality, which is done in sometimes linear, but now we've recently seen big leaps in terms of getting better interfaces in these materials by growing at lower temperatures, for example. But you also need device physicists like and others that can come up with new ways to make new mirrors, for example, for the lasers. And then you need to combine this in order to improve the devices. Yeah.
So maybe on the technology level, for the transferring this technology into markets and low-cost products. I mean, these UV LEDs are basically made out of the same material, gallium nitride, aluminum gallium nitride, that is used for blue LEDs and also for high power electronics. So the technology base is actually already there. You have to develop the devices, you have to develop the packaging, which is specific then to the UV wavelengths, but in principle, I mean, not only in principle, I mean, you can grow these on a larger scale on 4, 6-inch, 8-inch wafers and make mass production. And with the volume of those LED products comes also down the price. I mean, already we have ams Osram in Germany having a UV LED product, UVC LEDs at 265. And the roadmap here is clear. Basically, the volume goes up, the prices go down. If you buy a blue LED today, you pay only 10 cents for the LED, which can produce easily a watt of light. At the moment, the UVC LEDs that I mentioned with the 10% wall plug efficiency are still a factor of 100 more expensive per watt. But these prices will come down as the volume goes up. So next question over there. Yeah.
Hi, thank you so much. For Dr. Martina, you mentioned that there is no negative effect to prove that. Is there any positive effect, maybe something systemically or any change in the immune profile? Because it's known that.
That's a good question. So far, we only looked for the safety because we irradiated healthy volunteers. And here, there was nothing special observed, yeah? So that we had to take biopsies, so to look to the DNA damage. But I think this is something what we also know, that they make radicals, but in a low amount, which can be used for wound healing. Because wound healing is usually, if you have chronic wounds, they don't close because they need really some push to get to improve their immune system. And this is known for cold atmospheric plasma as well, which can heal this problem or also the wounds. And I think this would be very interesting also for this far UVC light.
Further questions? Maybe I have a question for Tanya again about the sensing applications. I mean, you mentioned a little bit measuring the gravitation. So in terms of applications and sensing, can you illustrate a little bit more in detail what does it mean in terms of sensors we could build with this technology?
Yeah, what I call so I guess you refer to either the atomic clock aspect. So there, sensing would be, how should I differentiate? If it's a purely atomic clock, I would call it more for navigation and communication. This is absolutely important and will be vital in future optical communications with high bandwidth and high bandwidth protocols. But then when you call it a true sensor, then it's like when I'm using my optical clock to bring it up on a mountain, out in the field. There's actually a big demand from geophysics for a good height reference. It's called the geoid. So what is actually the mass distribution on our planet? And that is even changing over time, as you know, from tectonics, volcanic eruptions, everything is changing. And the geoid is known to a poor level of decimeters. In a few parts, it's also centimeters nowadays. But even more difficult if you go to rough areas like mountain areas, islands, and so. And that's important for the hydrology, where's water flowing. Even a fun fact, if you want to build a bridge between Switzerland and France, they didn't manage to meet in the center because they had different height reference systems. So it shows a very simple challenge. So the geodesists would be very happy to use actually this high precision clocks as a permanent reference monitor of how masses are changing and what is really the gravitational potential of the Earth. So this is the sensing aspect. But beyond that, of course, we go really hand in hand with quantum computing. We build the same hardware, the same methodologies. And I would see this nanophotonic part in a mass or in an application where there's a lot of money on the market right now. This would be for sure first step, the quantum computer.
Okay, thank you very much. So further question from the audience. Seems to be... one more back there. Yeah, please.
Just as a follow-up to that, for quantum computing and sensing, what do you see as being the... do you think that for performance that it will continue to shift down to lower wavelengths, to higher wavelengths, into the deep UV, into the almost vacuum UV? Do you think that that's likely for sensing and for quantum computers, or do you think that there's a sort of a practical limit, like at 250 or 220, where you get the maximum benefit?
Yeah, at the moment, looking at the high potential candidates in quantum computing, it's indeed around the 370, 397, 313 beryllium is a good candidate, but it's not really stretching it to the vacuum UV, thank God. This is, of course, on the clock side, we recently discovered the nuclear clocks that operate at 148 nanometer. This is yet another step to go. In the far future, yes, but I think in the intermediate future of the next 20 years, I would see the lasers in a 300 nanometer regime. But that's already a big challenge enough, I tell you. So, and not only from laser side, because of course for a quantum computer, I could also afford a large laser with high power. But for us, the big challenge is the nanophotonics, the passives and the actives nanophotonics in terms of light conditioning and distribution, because the losses are terrible in photonics. So new materials need to be not developed, but I mean the materials exist, but they have to be optimized for low defects, low losses. The wall roughness of the nanophotonics, the etching processes is a huge challenge, because a lot of losses come in, and it doesn't help you to have a 1 watt laser and you have afterwards a milliwatt at the ions. So this is also not true scalability then to millions of qubits. Yeah, and also the resolution is a big problem. Yeah, I mean, if we're going now to wavelength of below 400 nanometer, we're really limited by the resolution the lithography can give us, at least in affordable fabs that are accessible to people who are not doing telecommunication mass production. So this is actually already a challenge right now.
Thank you.
For the use of ultraviolet light in the hospital environment, I think there is accumulated expertise over many, many years. How does this new part fit in the existing expertise? For example, I mean, to have rooms which are germ-free, the ultraviolet was already used. Has been decreased because of security concerns, or this is adding up? What is the present situation with the existing technologies?
I think the existing technologies only can be applied if no person is in the room, which is okay if you have time to clean, to do things like this. But if you have time pressure, or if you want to meet, even there is a pandemic, there is an idea. Of course, you have air cleaners, you have a lot we developed in the past. They are also do their job, but they are limited. And to irradiate the rooms in the presence of people, it's also maybe in emergency cars. You don't have the time maybe between, you know, if there's a pandemic, it takes a lot of time to get really rid of all the viruses. And maybe they can do it on the road to lower the virus. That is always, you cannot maybe get each germ, but to lower the risk of an infection is also to lower the amount of germs. And I think here far UVC can be used to you have spots, and you can in these rooms and all what I'm talking now, you can control the dose. I think that's very important. Public areas are critical. No? You never know how long people staying there, but this is the idea that you don't have to be afraid that people move in when you have your light on. And even there are more than one person, you will not spread it. It is an add-on, and I think it's a completely different use case.
Maybe I have a follow-up. You mentioned the two different wavelengths, this 222 nanometers and the 233 nanometers. Can you maybe explain why one is better, and for what is one better than the other?
Yeah. I mentioned now the 254, which is without people in the room, no persons, please. And the 222 is known to be even less penetrating. So this is good for air disinfection, because you don't want to go actually on the body. The 233 it penetrates a little bit deeper, but this means also it get microbes which are maybe not perfectly on the surface. Because I think the action that you kill the germs is known, is proven. But on the skin is not flat. Yeah, of course, if you look here, even if you're getting older, and wrinkles, but or even young people, babies, it's not flat. Microscopically, it's rough. So if you have maybe some germs hiding, with a 233, we are more efficient. Also, specific, we tested different components. If you have something, your germs in a medium, especially sweat, 233 is completely not affected by sweat. So on the skin, it's quite safe and also efficient. And if you go to other carbon-containing media, like mucin, like tears, then it becomes a little bit more complicated. But for this, you can irradiate more than one time. We will never maybe get rid of it at one shot. But if the idea, my dream is to have a tiny laser in a stick, putting in the nose, for example, and then killing the germs in the nose, and the people the other things to make the skin microbe-free, it's fine. You can clean it. That's good. It's good reachable. But I think this is a difference of these two wavelengths. Both are good, and at the moment, the 222, the lamps exist. You can put already in the room. And the laser additional, so there are three sources I think we would need.
Maybe I can add on to give you a perspective on the intensity and timing. You gave the dose levels, which might be a bit more hard to understand, but even with the current LED technology in the far UVC, with this illumination unit that we built, within 60 seconds you have reached that dose. So if you expose a patient with this light in 60 seconds, you eradicate 3 log or 4 log of MRSA on the surface of the skin. So it's quite effective already, and these devices are improving steadily, so hopefully that will be even faster and faster.
Yeah, I think this is not the problem. Technology is there.
Yeah.
We have to go the next step that we can use it.
Further questions? Maybe one to ask?
There's one in the back.
Okay, sorry, I didn't see.
Hard to see.
Thank you very much. I have actually 2 questions. Regarding the germicide power of UV, would you envision during a surgical procedure, to have some sort of short-pulsed laser during operation or after operation to clean potential bacteria in?
I would not, in this case, I think laser could be okay, but usually the germs which causes the surgical site infections, they come from the person itself, from the skin. And therefore, I would use LEDs or maybe 222. In this case, maybe the 233 LEDs, because they go a little bit deeper, because you don't need any chemical. Yeah, that's very convenient. You can switch on, because surgical side effects only occur if you have a long time surgery. So you can say, okay, the first disinfection is perfect. The microbes comes out from the hair follicles. There's a reservoir, and if they, after 1 or 2 hours, 3 hours, they come back, and especially if you put something into the skin, we have miniaturized techniques now. You can, if the first time when you get in your hip, you had a broad scarf, now it's very tiny, but you have to bring this stuff in without getting microbes in as well. And here you can really, during the surgery, irradiate the skin again, or whatever you see on the spot, and then it's antiseptic, so I think disinfected, and then that is the hope as well. Yeah, good idea.
And the second question is more to do with the UV lasers themselves. You've discussed applications for atomic clocks as well as quantum computing. There's recent efforts in nanophotonics for catalysis. Could you maybe mention some thoughts and insights on how the recent developments can aid in this field?
In the catalysis field?
Yes.
Then you would have to brief me on that, because I don't know the requirements for that.
Yeah, so basically there's studies that have shown that local hotspots created by nanophotonics assist in reaction rates, in chemical conversion rates. If you could mention briefly, because most of them have to do with LED light sources, but also to do with local nanophotonic antennas. If you have any thoughts that you could share.
So you're asking if the laser can be used to illuminate the nanophotonics so that it can create...
Yeah, and in which scale as well? How precisely could one probe certain surfaces?
Comparing LEDs to lasers?
Yeah, to conventional lasers, yeah.
So I mean, for the laser, you have these well-defined beams. So in principle, you can focus this down to diffraction limit. So this is a very small spot that scales with wavelengths. So the shorter the wavelength, the smaller the spot you can do. Compared to the LED, where it will emit in all directions, you can do a bit of a clever nanophotonics to tailor it a bit, but you can never go to the small spot size that you can with a laser diode. I don't know if that fully answers your question. Yeah, okay, we can discuss more afterwards, so you can outline a bit more.
Okay, thank you for all your responses and thank you for all your questions. We're coming to the basically wrap-up of this discussion session, and basically in the wrap-up you kind of summarize our findings or point of view, answering the question, what is the next step we have to take to break down the wall to deep UV innovation? And maybe each of you can give us your opinion on what we have to do in the next step. And since Martina ended, you maybe can start with a few first.
I think I already told that we get rid of the fear that far UVC is a bad thing. Maybe we need a new name. I would say have some fancy, sexy name that people say, okay, no UV inside maybe, and convince people to make a medical device that we could start, because I think it will be quite successful. You have also a lot of super infections in the dermatology where you should not touch, and this is easy to use, resistant-free, and we can apply it everywhere where it is necessary. And that would be my conclusion, I think.
Thank you. So maybe go to Tanya for her perspective. And
yeah, I focus very much on the material aspect, because the big fundamental challenge is what I have observed in the last years, how to bring the light to the atoms, to the application. And there we need much better materials. We have to get away from 5 dB per centimeter to 0.1 dB per centimeter. I mean, in infrared, everything works nice in telecom, but as soon as we're getting to the blue and beyond, it's a nightmare. And we have to open up more fabrication facilities for this high-resolution optical lithography, because e-beam lithography is not scalable. Yeah, and we need reproducible processes. You mentioned dielectrics and e-beam lithography is difficult. We need optical lithography of high quality with resolutions of 100 nanometer and possibly even beyond. That's the big challenge for the fabrication. I know in principle it is possible if you have millions of money, or if you're a large crowd, but so I would opt for multi-purpose wafer runs to bring together the communities. Yeah, we should talk to each other so that we have a rapid prototyping and development process.
Thank you very much. So last but not least,
yeah, so I mean, LEDs are a lot pushed by industry now, so we talked about that a little bit previously, so they will continue to improve these devices, I'm sure. When it comes to lasers, it's a bit more open, so there we need definitely to see strong collaborations between like material scientists and device physicists to kind of bring the best of two worlds together in order to make better devices.
Very well spoken. So I'd like to thank all three panelists for their contributions. And with that, I'd like to conclude the session. Thank you very much.
Okay.
Look forward to Basel.
Thank you all very much for joining. If we could have your... Thank you for being here. My name is Frank Locke, and I'll be the moderator or player coach in this session. Precision health, AI, how can it contribute to advancing medicine and obviously ultimately to patient care? Interestingly, we just had an extended round table with about a dozen experts in this field. We had some very in-depth discussions, and my colleagues here on this panel will try to summarize that a little bit. I have a couple of questions for the panelists, and then we look forward to your participation and to your questions. So let me give you a bit of an overview of what we just discussed, at least my 2 cents, so to speak. This was very much about integrating. Well, my perspective is we come from this quarter century of the genomic medicine. 25 years ago, the world was very optimistic. We would have the blueprint of life, the book of life, because we had the human genome. That those expectations were too high. It has delivered, but it has not nearly delivered as much as we were hoping. It turns out we need a lot more than genomic information, and we're not only talking about epigenetics and and transcriptomics. We're talking about proteins, eventually protein forms, multi-omics. We need multimodal information. We need interaction. We need structural data. We need spatial information. We need longitudinal time course information. So the complexities of the post-genomic era, if that's the next 25 years of understanding disease biology and doing better drug discovery, it's absolutely daunting. The complexity of information that we have, and by the way, the big gaps of information that we don't have yet, where we don't have good lampposts to get all the information that we would need, provides enormous challenges, provides enormous opportunities. It's a sobering reassessment of how much we know about biology and how much we don't know, and why our drug discovery success is still limited. Anyway, but it is the confluence with AI and deep learning. I don't think we could do any of what we're doing without AI and deep learning. AI and deep learning also isn't enough. We need good data. We need more complete. We need multimodal phenome information. And we're very focused on humanized data, much more so than mouse models or animal models in the past. That's my quick preview. And with that, I'd like to ask my 4 colleagues who were all on this panel earlier this morning to give us their 3-minute summaries and perspectives. And I'm old-fashioned, so I'll go with ladies first. Carolyn, would you start?
Very good, thank you. So what we discussed this morning, you related to it already, is we have a lot of data, yet we have very uneven data. We discussed that the early drug discovery space is really rich in multimodal data, and molecular data, like the clinical space, is starved for it. We have a lot of textual data, and we use AI on both sides for a long time. On one side, to gain a better understanding of the disease. In the clinical side, to increase the efficiency of process and reduce cost and go quicker. And there is this discrepancy now and this ambition to bring the molecular data and the disease knowledge to the clinic, not to go quicker and cheaper, but to increase the probability of success. So that was something we discussed. We also discussed that there are really pockets of excellence and building blocks in place to create virtual cells and be able to inform the clinic, but that for the moment, because this field is just starting, even so it advances quickly, they are very compartmentalized. So we discussed on how to bring the people together across academia, across hospital, across pharma and biotech and biobanks. And we discussed a lot about the AI evolution, so I can pass to Fabian.
Fabian, if you want to continue.
May jump in.
Yes.
So I like that sort of the original vision to some extent could maybe be, can we understand patient variation, right? I mean, let's say if any one of us goes to the hospital, either you don't want to be at the mercy of the current treating doctor and you remembering what type of sort of trajectory you had before to be actually diagnosed. What we actually want is some type of like a Google Maps sort of thing that tells us not just where we are with limited amount of data, where we can sort of then fill up all the other sort of missing modalities. In our case, we discussed about omics and so on, but it could be also all kinds of things that sort of goes there. So we don't want to just learn where we are, but also where we go. I like to call this patient landscape, sort of finding this type of state, but then also the type of trajectories that we roll down. In the sort of equivalent for cells, we often call this Waddington's landscape. You have heard about this. So let's say we have the Zugspitze. This is where sort of the fertilized egg cell starts, sort of rolls down the various valleys, and then sort of makes those different cell types that sort of makes up our body. I think similar to that, it would be nice to sort of have maybe some trajectory where it's sort of healthy, when then sort of we branch off into various disease states. And maybe we can also sort of understand those branching processes. Maybe we learn where those branching points are, zoom in, and then see what type of maybe mechanistic perturbation. So it's not just the map where we are, where the lanes go, but also how we sort of switch lanes. That could be a treatment, could be something prevention, but I think sort of putting this together. So how do we realize this with AI? For me, such a patient landscape, which is essentially a patient representation, it's a sort of classical machine learning type of problem, that could be the highest level in a multimodal, multi-scale foundation model. So this could be sort of the top thing of what we like to call internally a virtual human model, where sort of the top layer is a readout on the patient level. But then let's say you have something on the imaging or sort of organ side, something on the tissue side, something on the cellular, maybe even molecular side. What we have at the moment is that we have very good individual deep learning models. Those are often called foundation models, right? That sort of tie those layers together. But can we now bring these together? How can we bridge the scales? There's some first very strong evidences that these things happen on the sort of smaller scales. We and many others build virtual cells, and here's a true expert, Steve Quake, who has been pulling a lot of us in the community together to really build these. But can we then scale them up across it? And I think it's a fantastic sort of data-hungry type of endeavor. But if we can get that, this readout, this link to the phenotype, which is, I think, one of the holy grails in our field, right, could potentially be achieved with that.
Eike, do you want to continue before Steve disrupts us all?
Sure. Yeah. Yeah, let's bring us back to reality here. So if you go to the hospital, when do you go to the hospital? It's not when you're healthy, you're going to the hospital when you're sick, right? So that's a fundamental problem that we have. You wait until symptoms appear, and they say, oh, something is wrong, I go to the hospital. And then you have physicians, they look at you and say, oh yeah, you have this aches, and maybe some markers is up. But diseases are mainly phenotypically defined. So how do you make a model of phenotypes? You could do. It's not very helpful, I think. So we need to break those walls, basically, in medicine, because right now, medicine is not set up for what you want to do. But it's very nice that you want to do this, and I think it's the right way to do it. But it starts with the blood draw. If you take blood, the nurse takes blood, so what happens? It's sitting around, and then they collect a few things, and then they ship it to a lab that's maybe somewhere else, maybe in a different city, maybe 30 minutes away. So during that time, immune cells, which are important for the studies we want to do here, they will die, And then the other ones that are not dead yet, they respond to the dying cells. So there's nothing you can measure in terms of multi-omics, what we need for this type of data, if you do it with like standard way of practice at the moment. So that needs to be fixed, meaning this pre-analytics, you have processes from the blood draw to the analysis has to be short, has to be done always the same way, so you actually have reproducible data that you can then learn or use to learn this type of machine learning techniques. So that's one disruption we need in hospitals and physicians. And so that's important, though, because in the end, the other disruption we need is that the data that we all have, like we know our lifestyle, we know, our watches, not your watch, but your watch, they measure things all the time, but who takes those things into account? You yourself, there's a little app for it, but the physician would need to know, right? They don't have this type of data, and they don't know where you live. Well, they know, they can look it up. And if you look at the data from large trials, what makes you sick is the postal code. So where you live means how you behave most of the time, what the environment looks like. So all this type of data is not taken into account in hospitals because it's too late, and you always lived there. That makes you sick, and that was your lifestyle, that was your environment. So I think to really make truly preventive medicine or preceptive medicine, like we call it, we have to intervene much earlier. I'll give you an example. If you smoke, your likelihood to develop obviously cancer is higher, but also rheumatoid arthritis. It's the most important risk factor for rheumatoid arthritis. Why? Well, if you smoke, that means you have something in your lungs and the immune cells respond to that, and you make autoantibodies. And that 1% of you have this. 1% of the population has these autoantibodies, but you're not sick. You don't have rheumatoid arthritis. But over time, you get more and more autoantibodies, and then you develop the symptoms. We can now see already, 2 years before someone has disease, that some person will become sick and others don't. So we have predictive measures using omics to say this person is going to be sick in 2 years. Let's treat him before we actually is getting sick. So we do this with atherosclerosis, right? High cholesterol levels will make heart attacks or strokes. A third of the population will die from it. Look at your neighbor, one of them. And there's drugs you can take. You can take statins. There's now PCSK9 inhibitors. There's things that lower the amount of cholesterol because our environment is, is helping us to get sick. So I think we need to really rethink medicine, and then once these things are done in the right way, you create enough data that are good enough to train these models.
So we have an addition to the panel. Delighted to have Steve Quake from Stanford University here. I believe for some years you were also in the Chan Zuckerberg Initiative in a leading capacity, and you contributed this morning. Please contribute now with your perspectives.
Well,
Steve.
Thank you so much for the spontaneous invitation. I guess I'd start off by chatting a bit about one of the things you said this morning, which I thought was, really right on, and a shared belief that this metaphor of the human genome as the blueprint for the organism is completely incorrect. The proper metaphor is maybe it's a parts list, but we really—
A dictionary.
Yeah, exactly.
Yeah.
And, we really, despite 2 decades of having the genome in front of us, are very limited in our understanding of how to use it. And it's been powerful, but there's so much more to do. And the example I always talk about, and what I'll be the subject of my talk on Sunday, is even something as simple as trying to predict the cell types of the organism from the genome, we can't do it. It seems like in principle that ought to be a solvable problem, but we're not there yet. And the last decade of my life in the Chan Zuckerberg world was around trying to solve that experimentally. I mean, that was the motivation for trying to measure the transcriptomic cell atlases, to do experimental characterization of a molecular definition of all the cell types, because we couldn't predict it. And it's possible that, those data sets will enable us to build AI tools to do that, but we're at the beginning of that journey. And I think it's also important to recognize, we talked about this morning, that the genetics are only one component to disease, and trying to measure phenotype, or the things that have happened along the way, the things we ate, the things we were exposed to, none of that comes out of the genome. Like, I sequenced my genome 15, 20 years ago, and it says nothing about the effect of all the chocolate I love to consume and what that means to my health. And so these other, what you call multimodal ways of measuring, are very important in understanding our health states. It's not enough to look at genome or transcriptome, but to look at the proteins, the metabolites, the changes that have happened. And those sort of data sets together are going to be very powerful in sort of the basic science discovery of causes of disease and how to treat them. And AI tools are going to allow us to sort of integrate that together in ways we never have before. And that's like a revolutionary thing for science. The final thing I'll say is that part of it is sort of the discovery part. The healthcare delivery part of it, we talked a bit about this morning, is a different sort of challenge, in that how do you bring the fruits of those discoveries to the 8 billion people in the world who need their health treated? That's a different problem. There, the problem is, what's the least you can measure about a person in order to determine how to treat them because of the cost of measurement? That's also a problem that AI is going to be revolutionary for. It's a different sort of inference problem, but one that's equally important.
Yeah. No, I would add to that even, there's so much more biological information than what's in the genome or even the epigenome or the transcriptome. There's much more information there at different time scales, and it's a feedback loop. The central dogma of molecular biology was great because it clarified the primary direction of biological information flow, but it also has been, and when something's called a dogma, you should be careful, right? It has also done us a disservice because it obscured conceptually for many of us for a long time how much interaction there is and how much environment can interact with the phenome, and the phenome, we have reverse transcription and eventually integrase and whatnot, can actually modulate what's going on even at the genomic level. So, welcome to this beautiful new world. It's daunting, it's amazing, but it gives us so much more opportunity. So where are we in this journey from genomics to epigenetics, transcriptomics, the other omics is the spatial interaction, structural biology? Where are we in this? Are we 80% there? Have we gone from 10 to 20%? What are the big gaps? Would you like to, maybe in reverse order, we'll start with you, Steve.
I mean, just to jump off again from the central dogma, I mean, Crick's paper there, I went back and read it recently. He was concerned about information flow in a very narrow sense, just about information flow to protein synthesis.
Right.
We now know there's many other important aspects of information flow in the cell and in cell biology. And so it's a much more, as you were saying, a much more general problem we're facing now, and I think have the ability to take on and make progress with. And so I think we're in a revolutionary time in cell biology. It's sort of an amazing time. The discoveries are going to be just fantastic over the next decade. And many of them will center around these questions of information flow in the most general sense.
Yeah.
So I feel like we're not, I don't know if I could say percentage of the way there. The next decade are going to be amazing. Let's put it that way. I'll leave it with that.
Caroline, you want to give us your perspective? Where are we in this journey? How much do we know? How much do we not know?
Exactly. We know better what we don't know, to take somebody's saying this morning. We have loads to go. I think technically AI is evolving fast. We can do a lot of very cool things. The question is on what data do we do it? And it's true, we have a lot of molecular data in the early space. Most of these data come from cell line experiment where we have profiled the heck out of them. Coming back to the pre-analysis or pre-processing and how the samples are important, there was recently a presentation from Rebecca Gundry from the US. She's getting hold of human heart twice a week, and then she took 10 years to optimize a protocol where she can profile what's at the surface of the cell in there. And one of her main findings was you put those cells in culture one time, you passage them, you change by 50% what's expressed on the surface. So we need to keep in mind that we don't only need data, we need very good data to go forward.
Fabian, you're on a roll.
I think the dynamics part is fantastic, right? And it's so lovely to add. When we started to set out in the Human Cell Atlas, the sort of the spiritual successor, if you want, of the Human Genome Project, right? It was essentially enumerate all the variation in the human body. And, even there, we came up with some type of metrics to see when are we done? Because that's kind of what you ask, right? Like, how far are we? It turns out it's freaking difficult to actually be good about it. Like if you look at the first human genome even, right? I mean, what was the N number? It was like 3 or something like that, right? And still nowadays we're doing versions of GWAS and adding more genetics and sort of getting variation in. So I think there's always like another level of variation that sort of makes your complex, the problem sort of exponentially more complex. But I think so one thing, for example, we can, I think quite safely say is, let's say if we look at the blood or something like that, right? We have a lot of, let's say, single cell description of blood variation, including RNA, maybe some proteins. Of course, it could always be more, right? But I think in a control, maybe there sort of some type of saturation might be achieved with some type of modalities. But there's sort of new angles coming in. Within UK Biobank, for example, we're contributing to a project where now for 5,000 of those subjects, where you have all this deep genetic characterization, this phenotypical characterization, get also single-cell RNA-seq in the PBMCs. So even though we have so many PBMCs, you can sort of add that variation now on top, and you can start these additional analysis. I think what's important to say is, I think experimental space is exponentially hard. So even stuff that you can measure, but let alone what you can do to things, is something we can never even be roughly there. So we had just one paper where we tried to then fill up that space computationally. So we measured like 0.0001%, but then we went to all of Campbell and sort of added that by imputation. So I think we can never measure all of us at all time points with everything. Even that is just going to be a little bit. But I think the rest, it's quite safe to say that we can, with some sort of error, know maybe roughly where we are. And I think this might be more than we have. It definitely works very well for cell lines. So if you have a bunch of cell lines, you can, to some extent, impute to some others. We can maybe take this step a bit to organoids. And more recently, we had a paper together with a colleague from ETH, where we were able to sort of map them, in this case, brain organoids to also human development. So there are some links where you can also then start enriching also these more complex situations that, human developmental brains very hard to observe in reality. So do the perturbations on the organoids, transport them up with some error. I think it's getting there, but of course, small percentage.
Yeah, so you ask where are we? So I think we are not that far in terms of where we want to be, but still, in science, there's a lot of new technology, a lot of knowledge, and with AI, there's possibilities to really integrate data as we couldn't have done it before. But I just want to explain the gap between the science part and the vision that we have, again, with medicine. I used to be intensive care physician, so people are really sick. They have an immune problem, right? They're really sick. What do we measure? High CRP levels? How many blood cells you have? Oh, you have too many monocytes. It must be an infection. Not necessarily. Neutrophils, too little neutrophils, not good. So very rudimentary things are measured these days in the clinic, not just because only the pre-analytics, but we don't translate these things to the humans that are really sick in the clinic. And that's actually why I left medicine, because in the end, we just kept them alive as good as we could. Some fluids in, something for the heart, some pressors by drip. Then you pump air into the lung, put some oxygen in, so keep them alive. But nothing was done for the real problem that these patients had, which is an immune problem, right? And now we're at the stage where we really understand how immunity functions mostly. The cells, took like 100 years to find all the different cells. We know how they react. We know the components, why these cells react to triggers. We know their language. They make cytokines. They kind of communicate. If you interfere with the language, you have massive effects on many diseases. But there's a big gap between pharma development, science, and then medical implication. So if we only take a fraction of what we can do in science and apply it to the medical field, we would be completely different. We would have molecular information on diseases, not phenotypic. We would then say, oh, this molecule could be working in that disease. So we're a little bit in this direction in the cancer field, where you can now just sequence, and you have all these mutations, and say, okay, this is the kinase here, kinase there. Maybe this triple combination would be good for the patient. So we're kind of ahead in the cancer field, but in inflammation, and 75% of diseases are driven by inflammation. I'm an immunologist. So
75%?
75%, even many cancers. We're not there at all. We measure CRP and how many blood cells there are, like Rudolph Virchow have done it.
Yeah.
So that's a big problem.
So I'll do one more question from me as moderator, and then we'll turn things over to you. So get your questions ready. We've been talking a lot about humanized systems, right? How I deal a lot with oncology research and cancer biology, and in the cancer field, there's this by now old joke, oh, the good news will cure all cancers in the next 10 years in mice. And then 95% of the translation into humans fails. Of course, in neurodegeneration and many other areas, that's worse, perhaps. At least I guess our brain is very different from that of mice. That's somewhat reassuring. I also understand our immune system is quite different from mice, which is probably why so often why do we go to humanized models, whether they're organoids or organs on a chip or multi-organs on a chip? Some people try patients on a chip, and these chips get a little bigger. Why are these new microphysiological systems going hand in hand with this change or inflection point where we seem to be in working on disease biology and therefore on drug discovery? Since I mentioned the immune system, should we start with you?
Yeah,
we'll go in reverse order this time.
If you look at the amount of genes we have, right? We have exactly the same amount of genes than mice. But he looks different than a mouse. So why is that, right? But we have 270,000 splice variants. So we use these genes completely differently than the mice do, because they only have 40,000 splice variants. We have 270,000 splice variants. So what has evolved is actually not the amount of genes, but the utilization of the genes and the regulation of the genes. So that's why he looks different than a C57 like 6 mouse. So that said, if you now say, look, let's do drug discovery things and disease discovery things in a mouse, you completely fail the mission, because if you do it with him and a real mouse, it's very different. So I think that's the wrong model system. It can be used to look at mechanisms. They may somehow overlap. There are good examples where you have a one-to-one correlation, but there's plenty of examples, especially in cancer, there's no correlation, you know. So I think we need to query diseases. We need to do discovery science in human diseases. The problem is we're not inbred, right? We're not all like the same. In the mouse house, they're all inbred. It means that you then take out one gene and say, okay, what's the effect of that gene in the background of the same genetics? But it also means these inbred mice, they miss a lot of other SNPs and genes that may be contributing to disease. So I think that's a stupid model to even do science on. We need it, but in the end, it's not. I think we cannot understand mechanisms of disease by just doing disease models in mice, because lots of things are missing.
Jumping around a little bit, Carol, you
Yeah.
do a lot of organoid and maybe organs
Excellent.
on a chip at Novartis, right?
Exactly, and there's a huge shift in human sample and data first. But this said, I'm going to come in here. We all agree all models are wrong. Some models are useful. And I think for what we need today, we need to characterize our model and know what to use for what, because the virtual cell is far away. And by the way, that's true also for AI model. They're all wrong, but some are useful. Talking about organoid, one thing is to go human first, but the other one as well is to study perturbation in context. So if you perturb a cell line, you will see the intrinsic changes in the cell. If you perturb an organoid, every cell will be hit by that, but then the change in any cell will also affect the neighboring cell. And I think this humanized and in context is important. And finally, we're going human first because we can now, in some instance, generate human data based on reference data in position where we can't get access to it. And I think that's the whole promise of the field.
Anything you want to add, Steve or Fabian?
Yeah, I mean, let me say something in defense of the model organisms.
You as well.
Okay.
I mean, there's just certain aspects of shared biology that's not practical to do the experiments in human. Working out functional relationships often, because you can do perturbations in animals you can't do in humans. It provided enormous insight and discovery over the years. And it's a question of, I think, being selective about the questions you're asking, and asking questions about the universal biology that's shared across organisms. When we at CZI were building the first large language model, or a large language model transcriptomer on the cell atlas data, there was a big internal debate about whether it should be human only or across model organisms as well. And I pretty much put my foot down and said, we're going to do this across the evolutionary tree of life. And people didn't understand why at the time. But as we got into it, what we found was that we could use it to try to predict how experiments would transfer from model organism to human. Okay, so when you train across the whole spectrum, you can use it to try to predict what will translate and what won't from model organism to human. And I think these would be a great example of how AI can help us use model organisms more intelligently. I will say another example I've been involved in. I mean, in my lab, we've developed a number of liquid biopsy diagnostics, all that human from the beginning. So in that case, we wanted to be connected to the biology. It wasn't difficult to do the experiments. It was all about getting the human data. So none of those were done in any animal models. In therapeutic development, the case I've been involved in, both matter. I mean, there have been times when you just can't extrapolate, and it's going to be quicker to get the data in human, particularly around tox and things like that. There's only so much you can infer. Whereas for other things, like for cancer therapeutics, what combination of therapies might work, but too expensive to do in human first, and so you want to do some xenograft mouse studies to get an idea of which direction to go with the human trials.
Yeah.
Maybe I can briefly extend sort of on the method part here, because I think let's say we want to build a representation of just genomic variation, right? Like a language model of DNA, if you want, right? I think it's very clear that even though we have a lot of variation, right? I mean, what's our similarity? 97, 98%, or even more, like super high, right?
We haven't checked yet.
Well, it was good that I dressed up this morning, that you noticed that I look different from Black 6 mice. So this variation, in order to model like just a big DNA model, you need to do tree of life, exactly that. People like, there's a colleague at our place, he just goes through all fungi and sort of tries to understand how sort of various transposable organisms, whatever sort of comes together in order to really just build that basic core grammar of DNA. So I think that's very clear. Having said that, I think what we want to do is not just sort of the description of the state on our map, but also sort of how we move, sort of this effect of perturbation, this sort of where we go. This is going to get super large anyway, so I think it won't work without transfer learning. What we've been doing since the beginning of human experimentation is, and that's why I'm always fascinated when I talk to my experimental partners, like you have in your brain like this network of things, this is the next experiment that I need to do. So like any scientific theory is something that predicts how a model behaves under a perturbation, right? So that's why, if you know in a model system that there's maybe something, maybe you sort of draw this sort of maybe even serendipity-based type of parallel to say what you want to do in the human. So I think having some of these, we can even do it serendipity, we can even do the sort of computational to put some of this data together. But I think eventually like measuring what these things are, the validation, we need to then ideally do in something simpler. It could be organoids, it could be something in between.
Yeah, and maybe I can just add to that, coming back to one of your points, yes, we're far away from the human virtual cell to inform the clinic, yet AI is usually very good at one thing, is predicting what doesn't work. Now, if you think about a clinical team who are looking at what dose to give to patients, these models, even though they are not perfect nowadays, they can still tell them what not to do and what a okay starting point is. Obviously, the more you progress in the clinic, the more accurate you have to be, but for the first in human, they're actually already really useful.
Maybe just two more comments, rebounding on some of the things that have been said. On the animal models, I thought, well, maybe we don't fully understand the efficacy or the mechanism of action between mice and men. But then it's even thought, well, for toxicity, they must be pretty good, right? And it's absolutely remarkable as something as basic as DILI, as drug-induced liver injury, sorry, that's what DILI stands for, how much of that is tested in multiple mice and in one more animal model, and then there's immediate human interaction or liver toxicity. I thought something as basic as that you would get from the mouse model, but very often it turns out you don't, so there's some limitations. And my other comment, you mentioned splice variants. Well, I'm a proteomics guy, so post-translational modifications, isoforms, glycosylation, the complexity when you get to the protein level, the proteoform level is enormous, the heterogeneity, and not only between humans, but also us longitudinally, our different cells, if we have cancer cells or rogue immune cells, I assume, their glycosylation and other post-translational modifications are enormously different. That's where some of the limitations are. We don't have good lampposts that illuminate that and elucidate for us for us today. So there are many things that we can still do better, but at least, as you said earlier, Carolyn, we have a better understanding of what we don't understand yet. We maybe approach biology and disease with more humility today than 25 years ago, which is a good thing. And we have a lot more information. And we have this big 800-pound gorilla called AI in our corner who can really help us, give us a chance with all of that, with the deep learning. So good perspectives, thank you. At this point, we have a good 15 minutes for your questions. If you will bring a microphone to you, please briefly say who you are. Make sure you give us a question, not just a statement. And how I'm old-fashioned, I'll start. Okay, we start with the gentleman over here, and then we'll go to the ladies. Yes, sir, please.
Hi, I'm George Caputa. I'm senior editor at Nature. And I have dozens of questions.
I'm sure you would.
But I think that... no, it's Friday. I think that something, the preclinical and basic biology space has just exploded with AI and access to data. And I think we do a lot of talking about, as a clinician, standing in a hospital, what are your options for treating someone that's standing in front of you? We really need clear, I think, if we go back to how do clinicians get clear direction? as to what they can use, and those are from clinical trials, phase 1, phase 2, phase 3. Is it safe? Is it effective? Is it effective in a broad category of individuals? Do you think that the way that we are testing things through clinical trials and the design of clinical trials in terms of the numbers of people and how people are selected, do you think that really reflects the reality of the data that we have now? Because, you know, something that's so powerful is you have, you know, at Nature, we see these drugs come.
Maybe let me get to.
Yeah,
Can we
but I'm
take
just
that
saying, like, you know,
question,
like
that question,
60 years of research, and then all banking on this one moment.
Yeah.
You know? So I'm very interested to hear what you all think about how you can use the data that you're
You're
kind of
chomping at the
inform
bit,
that.
Carolyn.
Just to your question in particular on whether we select the right patient for the right option, my answer is right now not optimally, because we select the patient based on document and patient history, and we try to match it to molecular understanding. And I think that's about bringing together the phenotype of the disease with the mechanistic understanding.
I'll give you an example. If you have a little bit of fever and then your knee is swollen and the doctor says, "Oh, this is RA," what do they do? Give you some drugs, but then give you eventually TNF inhibitors because it works in 50%. And they say, "Okay, in 3 months come back and we'll see whether it worked." So that's empirical, right? So most of the compounds and drugs that are given are empirical. Actually, TNF, when first tested in sepsis, was a nightmare. You killed people. God. And this was almost the end of biologics, right? And there was a rheumatologist taking the drug and giving it to a patient that was really sick, and he got up the next day and was fine. So this opened up the entire field. It's all empiric. That's the problem. It's not all, but I think what should be done is you have symptoms and give the patient, and you control your own symptoms towards the treatment response. That's what you do in genetic diseases. But we are treating Gaussian distribution curves of patients that are phenotypically selected and not mechanistically selected. That's a big issue.
Yep. I'll go to the next question, and then I'm sure. Go ahead, please. Yes.
Thank you very much.
Would you get up and introduce yourself?
My name is Katrin Tedik. I work in Essen, Germany at the research center One Health, and I'm very happy that I get to ask my question about after the Nature senior editor, because I wanted to follow up on your commentaries on the models that we are using, because I agree that we should measure more in humans, and there are extremely powerful public data out there, for instance, in TCGA, right, and also other cohorts. And my experience is that when we use human data and we use them to validate mechanisms that we find in model systems, and we put them in our manuscripts, the reflex from the editors, including Nature,
and
is
the reviewers.
to ask me, no, actually not the reviewers so much,
Okay.
it's more the editors, who then say, "Oh, it's really great you show this in humans, but can you also show it in a mouse?" And yes, and I mean, this of course reflects also on science policies in the US versus Europe, where it's becoming more restrictive, doing mouse work. But I think it's really important that this changes and that we can measure more in human cohorts, and that using public data is gaining more values over the mouse models. And I don't
Did you want to
wanna
finish with a
discredit them.
question, or?
Yes. So what's your take on this? So what do you think, where we stand with the human cohorts and with the public data? How much can we do in there already, and where do you think are the data gaps?
So I can briefly take the data question. So I think basically also what George said, right? We're going to have, at the moment, very often we have one data set, one project, one paper, right? And we sort of typically move on. And I have the impression sometimes in pharma is like, if you have an old trial, you might not have measured this one or the other modality. You don't sort of put it into sort of one bigger thing. But we've learned, right, in these sort of big foundation and frontier type of models that we can kind of eat up the whole internet in terms of text and sort of just sort of suck it, smooch it together, and do actually something meaningful with it, right? And I think this is happening more in this. So I think clinical trial design, beautiful point, right? I think this is majorly changing. A lot of actually cellular AI people that there's a few big shots that moved to pharma. They actually didn't stay on the cellular side, but they actually used that information for clinical trial design. A whole bunch of startups go in that direction, where you can reuse then some of these sort of more basic things, some of their own trial, and then design new ones. So I think we're going to see a lot of this coming out.
Steve, I'll send things over to you, but maybe one drive-by comment. I think always asking for animal data when you find something in humans is nonsensical, because their biology, including their disease biology, including their immune system, sometimes will be so different that you may or may not find it in animals. Steve, over to you.
Yeah, I agree with that. I don't have a lot to add except to say that we're entering sort of more powerful era of using human cohorts because of shared medical records and things like that. So the ability to do discovery in humans is at an amazing time. And so for many things that previously required animals, we can probably go right to humans.
One more comment,
and then the lady.
So
the microphone, hopefully.
Big pharma has come together to write papers on particular mouse models that did not translate, because even if 5 different pharma companies take one mouse model with one gene identified as a target, it doesn't translate in the different places. So this is a little bit of a problem, because the microbiome has such an influence on disease phenotypes. So I think we have to really reflect on that. So we are using we're using Black 6 that are 2 years old, and we're just taking 500 mice as a discovery approach and look only as the variants. The variability of the phenotype is drastic. There's mice that are completely inflamed, has tumors, others are completely healthy, they have no gray hairs. So some mice have gray hairs, some are bold, some are not. And you can find out actually what makes boldness by just looking at the diversity, which is not genetic in this case, it's the microbiome changes. So that's an in vivo discovery approach that really makes sense.
We have 2 more questions. I think you already have the microphone, then we'll go to you.
Yeah. Hello, my name is Maria Chernachenko. I'm probably one of the younger generations here. I'm doing my PhD in University of Toronto. And as a part of my program, I have to teach, and I'm teaching a stem cell therapies course. And a question that my students often ask me is, why don't patients receive stem cell treatments in earlier stages of the disease? Because what we often see with stem cell therapies is that they're only allowed to be tested in patients that are terminal, where the potential benefits of the treatment will overcome the risks of it, and there is no other treatment available. But often in neurodegenerative disease, in a lot of degenerative disease where stem cells could be really useful in early stage, they're not allowed to be used.
Why
so
not stem cells earlier?
Maybe I'll start, and I'm sure you got something to say.
Yeah, just my point of my question is, how can we make it a safer and more approachable method to test certain therapies early on?
Steve, you can take that. And
so I think probably the most powerful aspect of stem cell therapies has been bone marrow replacement, right? Where if you've got cancer of the blood, you can get a new immune system. And that's an amazing success. I think it's been harder to show efficacy with other stem cell treatments. I mean, there's a lot of snake oil out there where people are doing injections in your knees for issues around there, where it's been very hard to show efficacy. And so I think it's just without the evidence, it's not going to pass medical standards.
No, it's exactly that, but also cost and commodities. It's very hard to make always the same stem cells. And
does it not work, or is it toxicities?
It just doesn't work. And there's probably toxicity too, but it's not working. I mean, you'll tolerate more toxicity if you're getting positive benefit, but I don't think it's been hard to show benefit from any of those.
Are there immune problems if you get stem cells from other people and stuff like that?
Absolutely, but you brought BMT into play, so you can use bone marrow transplantation in rheumatoid arthritis, in all these immune diseases that are autoimmune, like antibody mediated. It works, but it also kills a few people. So it's a risk-benefit problem here, right? Now we can actually selectively deplete B cells, and it's actually a revolution in medicine. You can cure lupus, for example, like a deadly disease. You can cure now with a single injection of CAR T cells. But even that is not a commodity. It's so hard to take cells and make this in vitro, and we ship them around in the world to get the right cells. But it's being done at the moment, and this is it's a field that is evolving. But now we can do this in vivo, inject something, so you make your CAR T cells in vivo, or take bispecific antibodies where your T cell kills the B cells. All these things are happening, but it's not a commodity yet.
I did observe that I heard anecdotally from a friend recently who is into this longevity research where you can get certain stem cell injections from, I'm told it's from Mormon women that don't smoke and drink, so that's good. And you can get it in Tijuana, just south of the border, where the FDA and maybe these things work. People come back rejuvenated. I don't know how much of that is psychological or not. But next to your question, please. Yeah.
Thank you. Hi, I'm Verena Haig. I'm a neuroimmunologist, and I work at Charité right now. So my question is related to how far are we really with this multimodal and multi-omics data integration? Because we have all these single-cell RNA-seq data sets, seq data sets, proteomics data sets, omics, epigenome, and so on. Exposome is a big thing as well coming up. And I'm part of a taxonomy group trying to actually settle down on a number and how to define microglial subsets right now, which already takes 2 years and is also funded by the CCI. But so I'm just wondering, how far are we really if we as a microglia field take 2 years to identify how many subsets we have, and we want to understand global disease and by integrating these
lots of silos, lots of walls that need to come down, but this gentleman is working on bringing them down. Aren't you doing this?
No, he's doing it.
Multimodal. Okay. Anyway,
we just make the samples. He analyzes them.
You're measuring them. I mean, I might start, and maybe Steve, you can chip in, because the Tableau, of course, examples are fantastic. So when we started, and I just sort of started maybe with the RNA side of things, right? When we started building these first atlases, there was basically, I think there were 30 papers around that said we have built a lung atlas, and it was always just n equals 3 to 5 patients or subjects, right? And then you sort of sample a little bit different pieces, and these things sort of just look completely different. So the typical thing, whenever you look at high-dimension data, what you always observe is that the major sort of source of variation is going to be where you sample, lab variation, and so on. So you need to have tools to bring this together. But I think the beauty of sort of advances in machine learning are that nowadays we know how to bring things together. And this now I'm just talking about one modality, but if you know how to sort of fuse this, of course, let's say if you have here 2 modalities, here just one, you can use this as a bridge and then sort of transfer over that additional modality to that. So when we build our first integrated human lung cell atlas, right? So we brought, I think, together up to 50 data sets now. We make a V2 where we have all kinds of diseases on top, where we really have then this observation. That sort of opens up really interesting new things where, in 2 diseases that you don't sort of look into each other, like maybe just randomly, maybe not. And I think we saw something like in monocyte-derived macrophages, there was one factor high up that was associated both in lung cancer as well as in COVID, because it was some type of scarring thing, which maybe even opened up new ideas for targets. So I think there's sort of these serendipity-based new things that you find there, which is kind of cool. And now you ask, like, when we, on the other hand, take so long with annotation, sort of curation, I think this is what you said with your sort of coach, with your sort of internal analysis, and be similar for us, annotating those clusters then takes really long time. Just this one point I want to make is that biology obviously doesn't care about what we call those things, right? Do we have now, I mean, when we started, we said, do we have 10 cell types in the brain or 1,500, as Stan Linderson or Alan Brain now claims? I mean, it's just like groups to different scale. We need to give them names, I guess, because otherwise every immunologist has their own sort of favorite name.
Exactly.
CD4, whatever. But I think the biology and maybe also the machine learning systems don't care so much about it. So for us to look into it and understand, sure, right? But I think for doing some type of prediction, it might not even matter that much. So you can even go ahead without maybe sort of fully describing things and giving nice names to things.
Any other comments, or should we take one more question?
I could maybe add,
if you could give the microphone back, please.
So to the question on omics, which is the best omics? Sidney Brenner was asked that once. What's the best omics? Proteomics, genomics, metabolomics? He says economics.
Oh, nice.
But to your particular question of cell type annotation, there's ways to do that from first principles. And in fact, Urilan and I have a preprint up on using Pareto optimality to do that, and I'd encourage you to check that out, because humans they're sort of motivated to find many different subtypes that may not be there. Immunology is notorious for this, because every new cell type was a new paper. So there was kind of a perverse incentive.
Okay, almost out of time. Fastest question ever.
Aisha Kisa from K Leuven. I'm in the Skeletal Biology Engineering Research Center. I'm speaking fast. I'm working in osteoarthritis model and non-union models, and we are trying to take it to bedside. So I'm going to ask you on the perceptions on the ATMP productions on the manufacturing side, because we talk about bench. Now I wonder your ideas how to take it to patients in the ATMP perspective.
Well, in our last minute, who has a good, who can answer this one?
No one.
No one.
No.
We're all looking at you as the pharma rep.
See, we're still in the dark ages. Well, that was a downer at the end of all of this.
Discussion. Longer discussion. I don't even know where to start to answer your question. So maybe we take that
offline.
Offline.
The answer is we do not have all the answers. Thank you very much. I think this was most inspiring and a vibrant discussion. I'd like to thank the panelists very much for their contributions. We thank you for your attendance, and let's bring down some more barriers and walls. Thank you very much.
Thanks, Frank.
these super dry lips.
Thank you very much.
So, thank you very much for joining this panel. And the question is, how resilient is innovation in pharma in the face of shifting geopolitical landscapes? And that's what's attracted you to this panel. My name's Chrissia Sommers, and I'm delighted to be moderating this panel together with 4 very distinguished panelists. So on my left here, we have Juliana McCall, and she's CEO of the California Council on Science and Technology. Juliana is a former Falling Walls Fellow, so from 13 years ago, and it's the first time that she's been back since. So, yeah, welcome. And we also have Gustavo Pesquin. So he is CEO of Ask Bio, a gene therapy company, and also a wholly owned subsidiary of Bayer. So welcome, Gustavo. And we also have Hendrik Strich. So our German colleagues, maybe you recognize Hendrik. So was a former advisor during COVID and is now actually member of the German Bundestag and federal government commissioner for drug and addiction. So warm welcome. And last but not least, we have Alice Aiken, who's come all the way from Canada today, sorry, from Dalhousie.
You have it coming here.
And Alice is a professor of health and also former vice president of research and innovation. So a warm welcome to you all, and thank you very much for joining us. So let's start with an icebreaker question to all of you. So in this world of shifting geopolitical landscapes, very, very exciting times at the intersection of science and biotechnology, what do you see as the greatest opportunity? We'll start with Julianne.
Thank you so much for having me. Working at the intersection of public policy and science and research, you can't help but see the multiple factors that are influencing the outcomes of our work. And so my contribution would be to appreciate the actual needs of society and not continue on with the status quo as if there wasn't greater diversity in the research pool than was originally architected.
Very good point. Thank you. Gustavo.
Thank you and good morning, everyone. I would say that the speed and the accuracy at which therapies can be developed these days was unthinkable only 10 years ago, and I would say that this is a massive opportunity for humanity to find cures for diseases that have been stubborn to find a relevant therapy.
Thank you. Hendrik.
Well, I think in a time of crisis and shifting geopolitical landscapes, it's time for science diplomacy, and science can be a bridge, a neutral intersection between countries, and can actually help, even though there's a crisis, can help to shape the world still to a better place. And at the same time, I think Europe can play a particular role in there, because it can be a safe haven for some of the researchers that can't do their research right now in other countries.
Thank you, Hendrik.
Yeah. Thank you for the question, and for my colleagues. I agree with all of you. I'd like to put in a plug for Canada also as a safe haven for research.
We accept that.
Yeah. You know, I think for me, one of the greatest opportunities right now is the opportunity for everyone to come together, for governments, for businesses, for funders to come together and scale. Start scaling quickly. We have the solutions. We take way too long to get them to market. So I think the opportunity now is for scalability, and I think it's exactly the right time when we realized we've had a reliance on maybe traditional academic norms and traditional funding sources, and we were okay with a slow pace, and that's all shifting, and so now is the time. Now is our opportunity.
Wonderful. Thanks, Alex. So we have speed, we have diplomacy, we have collaboration. And I did pick up on you, Gustavo, you're waxing lyrical about gene therapy. Why is it so exciting right now to be in gene therapy?
Well, thank you for the question. I would say that gene therapy is in this intersection of several breakthroughs in terms of innovation. I think it was probably not only the ability to create more effective gene therapies, which is a field that has probably already 30 years by now, but also, for example, the fact that we're tackling pathway diseases, because gene therapy was conceived for diseases that had a clear monogenic root, and maybe everyone thought about those rare diseases when they thought about gene therapy. Now, for example, in AskBio, we're developing therapies for Parkinson or heart failure using the same platform. I think that also many times something that is overlooked is that when you think about gene therapy, the route of administration also is a breakthrough. Like, for example, all the work that we do in brain, which from a pharmaceutical standpoint has been an innovation graveyard because a lot of promising therapies failed. But now the fact that you are delivering that effective therapy in a surgical procedure exactly in the part of the brain where you want it to be, that delivers a degree of precision that was, again, not possible many years ago. I would say that these are probably the breakthroughs that are right in front of us right now.
And I really like that example, Gustavo. So you're talking about precision oncology, but when it comes to Parkinson's, it has to be so precise. Yeah, as you were saying, it's really, really exponential developments. So, Julian, you're also here from representing California. How is the vibe there right now? And if we think about international ecosystems and making sure at the end of the day that the drugs get to the patients as fast as possible, how are things developing?
I do appreciate that Europe and Canada are safe havens. We try to see California as in a similar light. We are leaning into partnerships, recognizing that through more expanded data sharing, of course, always prioritizing patient data privacy and security, but acknowledging that we all have a piece of the puzzle, that coming together is possibly our only way out of this moment of tumult. So I would leave you with that.
Very good, and it's also, I mean, I like the part about the puzzle. So it's, if we take this holistic view, it's a very systemic, moving landscapes, as we mentioned. And gene therapy, we spoke about Ask Bio. Now, looking at how things are developing in the States for gene therapy, last year, or I think it was 2023, there were 2,050 clinical trials only in gene therapy. In Germany, we had 150. So, Hendrik, why is this? I am aware we have Medical Research Act, we also have a cell and gene therapy strategy, all good milestones going in the right direction. First of all, why the delta, and are these strategies helping?
Well, let's start a little bit with a historic background, because Germany used to be the biggest insulin producer. And I think it was a wrong political decision at that time to make very strict gene therapy laws. And we still have those laws in Germany. And it's unbelievably complicated to bring, for example, CAR T-cell therapy on the market in Germany. But the good news is we have realized that we have problems there and that we have to modernize those laws. So I hope during this period of government that we're going to manage to renew these laws. I think it was a bad decision at that time, and it basically broke the company Höchst, who was producing insulin at that time. Germany has a problem with clinical trials right now, and even though we have the Medical Service Act right now, it's not enough. During COVID, Germany had 65 clinical trials. 51 of the 65 clinical trials were cancelled, and the average participations in the clinical trials were only 15 participants, which shows the dimension how bad Germany clinical research is right now. It's overly bureaucratic. We have a complicated ethical system right now. We have 16 states, and sometimes when you do a collaborative study, every ethical committee has to vote on it and has different changes it would like to see. Now we have changed this with a new medical service law, but it's not enough. It didn't change the landscape that well. It's still overly bureaucratic, and we have to work on that even more, make it simpler, make it easier. One study, one ethical vote, etc. That's the way we have to go to bring more medical research onto ground in Germany.
Thanks, Hendrik. I found it very fascinating. You shattered my illusion about Germany in the COVID times, because I actually was under the impression that bureaucratic hurdles were broken down. There were no silos. BioNTech was hailed as, you know, a pioneer out there, and Hendrik was no. So
well, I'm not saying we had good research, but doing clinical trials, and in particular doing clinical trials with new substances or with vaccines, we were not really able to do this in Germany. And for BioNTech, for example, as a German company, they went to other countries to do the study. It was not really much performed in Germany here.
Okay, so we've spoken about the US, Germany. Obviously, we're here to talk about geopolitical landscapes. To what extent is China playing a role here? And I know when it comes to speed, they seem to be a lot faster as well. So what are they doing right, would you say? Anyone can answer this.
Money. They're just putting gobs of money into research, right? Yeah. So it's, I think our funding systems, and all of us, Europe, Canada, we all relied as well on US funding. Yep. That isn't there anymore. Mm-hmm. And I think we have seen a government that will put loads of money into research and build big facilities, big research facilities in record time. And so, you know, I think if I was to say that's what they're doing right, I think that's what they're doing right. They're funding the work.
I think that's one aspect, and we also spoke. Gustavo,
sure,
go
no,
ahead.
I will agree with that. I think that there are several ways in which they are supporting the evolution of innovation. Another one is the way that they prioritize it. Like, for example, when it comes to clinical trials for rare diseases, they are very supportive of what is called the IITs, the investigator-initiated trials. And now you're starting to see a lot of therapies for rare diseases that, in partnership with these patient associations, they are tested much more rapidly in China than in the rest of the world. I also want to highlight the power of innovation that is being seen in China these days. Bayer opened one of those collabs, one of those incubators in Shanghai a year ago. I was privileged to be there for the opening. And for example, we have developed with one very successful gene therapy company in China a partnership because, for example, in the world of gene therapy, different from traditional pharmaceuticals in which someone identifies one compound and it's okay, who did it, but that's where the story pretty much starts and ends. A gene therapy is a combination of a capsid, a transgene, a promoter, a route of administration, sometimes immune suppression approach. So we're discussing before the session today, and pretty much I cannot think about one therapy in which we do not have one partnership somehow embedded in it. And in that sense, China is playing a strategic role in innovation.
Very good. Comes back to the topic of the collaboration, the ecosystems. Anything to add, Julianne? There?
I mean, I see echoes of the U.S. National Laboratory System, where they established user-facilitated sections of the laboratories where you have particle accelerators, right, for use by academia for free, of course selected through a competitive process, and by companies, right, when the data are proprietary, right, there's a fee added onto it. And I see, right, China for 20 years now, right, invested heavily in genetic sequencing technology to ensure that they had state-of-the-art facilities for their academics and their businesses to use in tandem. And I think we're seeing the benefits of that. The National Academies of Sciences, Engineering, and Medicine in the United States have put together 2 state-of-the-science addresses last year and this year. And pulling in the numbers, China is already producing more high-quality research articles than US science ecosystem. Not just more articles, more high-quality articles measured by the number of citations. So we, I think, are seeing the benefits of that early infrastructure investment.
Okay, that's very, very interesting to know how things are developing, and also this innovation-friendly frameworks, which we've seen in the States as well, yeah? And just coming back to your point about money, yeah? So venture capital actually supporting startups to thrive. This is also a very, very exciting topic, which we see in California. What's the secret sauce?
I mean, not being afraid to take a chance, right? Recognizing that of top 10 out of the top 10 candidate drugs, only one will be successful in the market, and so having that ecosystem ready to go and within proximity, right? We see through published literature that when scientists, engineers, administrators, right, are able, not to mention, all the administrative supports that make that system possible, when they are within, I'm going to say 5 miles, forgive me, I think it's 9 kilometers of one another, right? They see an exponential, thank you, 8 kilometers. They see an exponential, a quantum leap in productivity and creativity in and through their work. So we are seeing public universities like the University of California investing in student projects as its own form of a venture capital source. So trying out new things and being within proximity to have that cohesion within the network already so that you are ready to jump when the time comes.
You can see the younger members of the audience here, eyes lighting up, wow. So, Gustavo.
Maybe what I would like to add is that pretty much when you look at the success of the US in the world of biomedical innovation, everyone focuses on the venture capital world, the role of the NASDAQ, but something that is really overlooked many times is that connectivity between the NIH funding and the academic institutions. This has been pretty much the main source of breakthrough innovation for the biomedical ecosystem. And let's say that all the challenges these days with the federal funding are putting that ecosystem at risk. Something I wanted to add now, because it's connected to the previous question, that I think it's an important question for societies as well, is the role of education in science as well. Like probably if we look at why China is successful, you go to China and the bright kids want to be scientists. I have 2 very intelligent children, and every time that I speak with their friends, almost every other time I have to ask, why do you want to be a banker? Why do you think that the world needs another banker? You're so intelligent. There are so many wonderful things that you could do for the world. And I think that it was interesting because that was my personal experience, but I think that a couple of weeks ago there was an article in The Economist, I believe, about this. It's like why all the intelligent kids in the US want to be bankers or consultants.
Yeah.
So I think that by itself, I am completely sure that is playing a role in the success of China compared to the Western world.
So in Halifax, Nova Scotia, so we're on the east coast of Canada, for those who don't know, and Dalhousie University is one of the research-intensive universities in Canada. And we are in a province that, and a city that has become a startup city, I would say in the last 7 years probably. And the university played a really key role in that, as did the venture capitalists and all of we built this incredible innovation ecosystem. So it started, we're right on the Atlantic Ocean. It started with a lot of ocean-related startups. There are over 400 ocean-related startups in the city of Halifax. It's a city of 500,000 people in a province of 1 million people. So we're not big, but we're small. And that's our advantage. It's because we are big enough to have impact and small enough to be nimble. And so the government has supported this. The venture capitalists and the private sector has supported this. And Dalhousie University now leads the Lab to Market program for Canada, which is like I-Corps in the US, the innovation programming. And so we were really able to contribute to that. And there are now, do you know the number of startups in Halifax, Parmjot? I'm looking at my colleague over here. Yeah, something like 876. About 876 startups now in our city, and we got so much attention now. We're the North American hub for NATO Diana, which is the Defense Innovation Accelerator for the North Atlantic as well. So we got to be part of watching an ecosystem start up, and we looked at Silicon Valley and said, all the smartest people aren't in California. They're all over the world, and what they have is the right ecosystem. ecosystem, and we need to mimic that ecosystem, and we've done it very successfully in Halifax, and I would say that others can do it too. It's possible.
So just zooming back also to Berlin, I think it's really, really inspiring what's happening also in Canada. Berlin also seems to be a growing innovation hub. And, you know, we hear expressions like it's a Boston on the spray. Hendrik, is it working? Is it headlines? Do you feel the vibe?
Well, I think we have in many different countries or cities in Germany, like those little ecosystems that are happening for different in different research areas. Here, of course, with Charité, Berlin Institute of Health, we have the Robert Koch Institute here. So in the biomedical area, this is really something that seems to work. We have also in my city where I'm coming from, we have in different areas like mathematics, for example, we have a huge ecosystem, physics, mathematics for excellency. Like we have 9 of the bigger clusters for excellency. It's the largest cluster of we call it elite research in Bonn, but what we are lacking in is really the step for funding a startup, or like the first step maybe to start a startup up works, but it's again overly bureaucratic, and we have complicated application processes and complicated reporting processes, and but we realized this, and that's why that in many of those fields in Germany we realized that we are actually putting a blockade of letting the science do their job and trying to bring it onto the market. So, and that's why we even have a ministry now for that to reduce bureaucracy and modernize the country. I hope it's working, but I think the first step to do something better is to realize what the problems are, and I think we're at this point right now.
And we do, just wanted to jump on there, we do have very good positive examples of public-private partnerships. So, for example, recently the opening of the Gene and Cell Therapy Center in Berlin, which is a partnership with Charité. Gustavo, do you want to?
Sure, I can comment on it. Particularly, our chairman was Stefan Ulrich, was heavily involved in that project. This is a good example of a public-private partnership work. It's basically something that was done between Bayer, the Charité University Hospital, that there's a name in German for that, I'm not going to even try it, and the Berlin Health Innovation Center. And it's currently partly funded by the state of Berlin and the federal government, and we're discussing sustainability of those investments. Yesterday I was in Paris, and there are multiple examples on how, with creativity, this can be funded. Like, for example, the center of the public center of gene therapy there is called Geneton, and the reason for that was that the Geneton was the TV show that raised money to find cure for rare diseases, and basically that became the structural way to fund the center, the National Center for Genetic Diseases. And it's a fantastic center, 250 researchers. This is a cause that is close to the heart of the French, so every year, the same time of the year, they do the fundraising and people donate serious money. And that really shows that, in a way, we discussed this before the session as well, how this intersection of technology, government, and society, that is what can create a little bit of the magic chemistry or the barriers that can stop innovation.
I love that. It's a very, very good positive example of also the societal pull and the way you're getting everything intermeshed, as you mentioned, the governmental, academia, industries. You wanted to add on to that?
Yeah, thank you very much. We keep referencing ecosystems and the benefit and value of ecosystems. And as someone who's worked in California state government for 8 years, in the governor's office as well as the California state legislature, government is often left out of conversations around investments in science and technology. I have one wonderful example. Within 3 years of the California state investing a modest amount, $2.5 million, for an 18-month project demonstrating the economic value of whole genome sequencing for infants, newborns with rare diseases who are otherwise difficult to diagnose. And within 18 months, across 5 different centers in California, the researchers led by University of California, San Diego, determined that it was economically beneficial, right? Not just health beneficial, but also economically beneficial to the state. And within 2 years of the conclusion of that study, the state of California started supporting whole genome sequencing of hard-to-diagnose newborns. It was a no-brainer. They saw the numbers, they realized, we need to do this. So engaging government during the research process, right, to determine, and modes of access, right, will be dependent on government support, and government is often swayed when you actually put together a proposal that speaks not just to the science, but also to the societal factors.
Hendrik, how can we take a piece of this? Are you inspired now?
Well, I think we are actually trying to do this more right now, because we started founding think tanks within our party, within the Christian Democratic Union, and we have those think tanks around science, research and innovation now, where we invite stakeholders from different parts of science, and not to have the immediate solution what we have to do next, but to think outside of the box and maybe rethink how we want to fund science, how we want to help science to be the leader in new ideas, in changes in society, how we can actually maybe break down how the models of science and science careers. In Germany, for example, we have this problem. We have either students or professors. The postdoc time is rather short, and we don't have really staff scientists or anything like this. So some researchers do not want to become professor, and we want to think about, together with the scientists, how we can change the scientific environment, that it's better for the scientists, and also maybe we have a bigger impact and new innovations.
Professor Alice Aiken, I think there's a lot we can learn from you here. So also in terms of public-private partnerships and inspiring young people to go into academia.
Yeah, and you know, it's interesting. I took a very circuitous route to academia and didn't actually start in the academic world till I was a bit older, but you know, there's a couple of things. I think we need to teach our scientists and our young scientists how to communicate properly, right? So Julianne gave us a great example of communicating back not just the science, but the economic benefit of doing something. And that is what people want to hear. Mm-hmm. We all find our science fascinating, but don't get up and bore politicians with tons of data and things that they aren't interested in. So I think we really do, which is part of the reason I love Falling Walls. It really teaches people to communicate in a way that everybody can understand. So I think that's really important. I want to give you an example of really great government engagement. So Canada has universal healthcare. We don't have socialized medicine, we do have universal healthcare. And our government, and it's run by each province, so that presents, there's no real federation, presents a bit of a problem. But in our province, the government funded a health innovation center. And it's called the Nova Scotia Health Innovation Centre, and they adopted a test and try model. So they brought in some big companies, some startups, the academic ecosystem, and the government. And what they said is, if we try something in one area of the province and it works, we will implement it across the province, because the government pays for healthcare, so they can do that. And it has been so successful that the CEO of our health authority now is getting requests from around the world to go and speak about how they did that. A lot of us had a piece in how that started up and got working, but it is a real success story of what can happen. And I actually believe, really well aware that I'm standing here with a lot of health people and a physician, and you know, health is the hardest nut to crack. It is really the hardest nut to crack. We're working on a pan-Canadian ethics approval for clinical trials, right? Because right now it goes province by province, so we're almost there. We're almost there. But you know, I think health is one of the hardest nuts to crack, and I think we've got a really lovely model in Nova Scotia that seems to be working well, and a lot of it's about communication. Yeah.
Very good. Maybe just one aspect, because we talk about economic benefit, and I did read an article the other day in Financial Times. The headline was AI is bucking the international trend when it comes to healthcare. This is the one area where it's seen viable as actually being profitable, beneficial for the states, for the economies. To what extent are we weaving this into our models?
Good question.
Extensive.
Unprepared question, sorry.
If we miss this opportunity to leverage our technology in a way that benefits both industry, academia, as well as the patients, not to mention government, in administering all of these programs, will be foolish. And it's not so much the deployment, it's the responsible deployment of AI, particularly with healthcare. I would say that we can't move fast enough, but I'll reference my initial comment during this panel, and we can't just keep doing business as usual. There's a social scientist in New Jersey, Princeton, New Jersey, Dr. Ruha Benjamin, who conducted some social science about 2 years ago and found that with every biotech breakthrough, health disparities in the United States worsen. That the system wasn't built to lift all boats. And I think with AI, we actually have an opportunity to make good on our promise of deploying precision medicine, and that gives me immense hope, with the understanding that we are applying those responsible levers appropriately.
Exactly. So, I mean, the topic of this discussion panel is resilience in pharma, speeding up breakthrough medicines from the molecule or from the therapy to the market. And yeah, AI must play an important factor here. So it's interwoven into everything now. So Gustavo, you were making a point earlier today about this, yeah?
Oh, yes. And I think that I'm a complete believer that this is the biggest transformation in the history of the world. This is not a buzzword. It is. I would say that probably for us who work in this health system, last year was a very important indication, because if you see who won the Nobel Prize of Chemistry, it was not a chemist, it was not even a biologist. It was an AI expert who said, if we can teach a computer how to beat anyone at chess, and if we can teach a computer how to beat them at Go, that it's a lot more complicated, why is that the world has not been able to understand how proteins fold? And there has been a plateau that was reached at kind of like 20% effectiveness in the discovery. And with the exact same approach, they took it from 20% to 90%. This is AlphaFold. And by the way, what was incredible is that they created the system of open innovation, and it was like in a matter of weeks, AlphaFold had about 100,000 users in the world. So that's why I'm saying, like, the speed and the accuracy of innovation is not just a concept that looking at you go to the hard facts, and it's a complete Big Bang. And at the same time, I'm very convinced that there are risks associated to artificial intelligence, and I think that probably it's funny because 25 years ago we were talking about the importance of the collaboration of industry and government and academia and all that, and it was important. But if you tell me, okay, but can the world keep going if we continue the same way? Probably the answer was yes. It was going to be inefficient, but yes. I would say that we have reached a point in which this can start becoming very, very problematic if there's not like a great collaboration, a shared vision from the technological side, the regulation side, and the ethical and society side. That platform needs to be consolidated in an effective way.
Well, I totally agree. But one aspect, I think it will completely transform medicine from small molecule design to diagnosis and even finding cure for some of the diseases where we couldn't find a cure yet. One aspect that I keep thinking about right now, as a federal commissioner for drug and addiction, we keep discussing right now if we're going to have a transformation in the world of drugs, illegal drugs, euphoric changes in different euphoric states, etc., because we're getting closer there as well, that we get designer drugs where we can't really think about yet, or that we have better affinity to the receptors that will totally transform the world of drugs, and therefore we may have different different addictions where we can't really think of yet, designed by AI.
Mm-hmm. Is that something that you're looking into already, Hendrik?
We are discussing it. I'm also in the European Drug Agency Executive Board, and we are discussing this a lot, as we are also seeing a lot of synthetic design opioids, for example, nitazenes, morphine, which have a potency of 500-fold of regular heroin, and so small molecules can already be deadly. And so we are small amounts. So we are discussing if we are just at the brink right now of a totally new development of synthetic drugs, but we don't have clear evidence for that there's a totally new market happening right now.
Did you want to build on that, Alice?
Yeah, I do, and I think there's a more positive side to AI, though I'm really glad people are thinking about that. But
Oh, don't get me wrong. I think AI is fantastic.
Yeah,
That's why I said the whole part about medicine before, right?
No, so what I really think is going to change, and Julianne brought this up, but what I think is really going to change with AI, or what I hope is really going to change with AI, is a focus on personalized medicine and health equity. So that no matter where you are in the world, so I come from a country, I live on the east coast of Canada, it is faster for me to fly to Frankfurt than it is to fly to Vancouver in my own country, right? I live in a large country, small population, rural and remote medicine is very important to us. And I think that having that health equity is one positive aspect that AI can bring. But I also sort of go down the route of, if we really have personalized medicine with AI, can we not then also cure addictions? Rather than better designer drugs coming out, like, could we not then actually cure addictions, which I'm pretty sure most addicts would want? So, what I really hope with AI is that the future is bright for all of us. We all have the exact care that we need at the right time, the right amount that can sort us out, and anyone has access to it.
Yep.
Yeah.
And adding further context, right? 85%, when you predict someone's health, 85% of someone's health is attributable to the social drivers of health, the social determinants of health.
Postal code. There's
right?
code. Yeah.
Exactly, right? Where they live, where they work, their education status, right? Their income, right? And for AI, right, to capture the complexity, right, of those factors gives me immense hope. I'm right there with you.
Yeah.
Mm-hmm. Okay, we've really kind of dug deep onto many, many different layers and topics here, from collaboration to venture capital, and now weaving in the power of AI for the future. I think this is a good time to open up to the audience. We already have the first question there.
Dr.
In the middle on the left.
Eric, I think Eric, you, yeah.
So my name is Talia Milenki. I am from Goethe University. I'm a researcher in medicinal chemistry. And first, thank you for the thorough discussion and for covering so many topics. I would like to relate to one of the topics that was brought up, why the younger generation is not that interested in going into science.
Yes.
And I will say, unfortunately, as a medicinal chemist, I have very brilliant colleagues, some colleagues who just finished PhD. And we are facing really hard way of searching for a position.
Mm-hmm.
Even between us in the lab, we say that the market is overfloated. Yeah. Nobody needs medicinal chemists, and I will actually disagree, and I will say that many of us stay as postdocs because it is simply more convenient. And my question would be, is there any way to overcome this? Are there any plans to somehow change the situation? Because indeed, there are so many brilliant researchers that I think can contribute tremendously to innovation and innovation in medicinal chemistry and in small molecules, for example.
Who wants to answer this?
I can get started, and thank you so much for your question, because also from your experience, you bring the reality that probably was behind some experiences that I have lived. I would say that probably an answer may have multiple components. No, I think that probably funding in healthcare, I know that we have many people from the venture capital world here, has been a crazy roller coaster, because we came from 2021, beginning of 22, in which the good, the bad, and the ugly projects will get funded. If you had an idea, you got the money, to a point in which funding got dry, literally from, like, for example, we were following because of this partnership approach that we have, gene therapy companies coming out of stealth in the United States, and you look at like 15 years, like from the early 2000s to mid-2022, and there were like systematically 14, 15 companies coming out of stealth per year. After that, there were like 2 in the following 36 months. So probably I'm sure that a lot of scientists these days are starting to feel how fast the funding of innovation has dried up. The other part, of course, is that this goes in neighborhoods. Clearly, innovation in one country, sometimes within the country, is very different. Sometimes one is faster and probably with more opportunities to grow. Others are probably less vibrant, but a lot more stable, and stable in science is good as well. So I think that probably one additional challenge is that, probably a scientist may want to consider where in the world they want to develop, and this has social implications as well. Probably to leave you with a happier note is that clearly we are seeing the funding of innovation turning the corner in the past 1 or 2 quarters. Like if a lot of companies that ask me March, April, where we are, I will have told them, this is a dark, dark night. Like it's been dark for 3 years, and I do not see the light at the end of the tunnel. If you ask me in the past 2-3 months, the friends who were in good programs, I have one of them who IPO his company yesterday, Evomune. Another one, Trogenics, that is a former AskBio colleague, raised $150 million a month ago. A lot of very competent colleagues that were calling me, hey, I cannot find my next role. They're landing
Gustavo,
a job.
I'm going to have to interrupt you.
Oh, sorry. Sorry.
Because we don't have much time.
I
but I think
that's my Argentine side. We're long-winded. Genetically long-winded.
Really, really good to see that,
Very good.
You do see a little light at the end of the
I
tunnel.
do.
There are positive examples. Alice, very briefly.
Very briefly, with my Vice President Research and Innovation hat on, I think we do our PhDs and postdocs a disservice by not teaching them where else they can be employed. We were trained to be in academia, and so we know how to train people to be in academia. And I think we really need to train our PhDs and postdocs to look at corporate partnerships, to do internships in industry, to do internships in government, and look at being in policy. So to look at other opportunities. Nothing makes me more sad than somebody who feels like they have to be stuck in a postdoc. There are so many opportunities for people with PhDs. We live in the knowledge economy.
Excellent.
Yeah.
So my organization, the California Council on Science and Technology, modeled a state-level science and technology policy fellowship after AAAS, the American Association for the Advancement of Science, which has been placing doctoral-level scientists and engineers in U.S. federal government for 55 years already. And there are over 200 of us alumni. I personally spent 16 years in academia, thought all I had to contribute to the world was microneurosurgery for rodents. I really thought that's what I had to offer. But my goodness, you take that same scientific approach and you apply it to the tens of millions of people of California, in my case. Data are data. Whether I'm looking at a genetic assay or services rendered across California communities, data are data, and over 100 of us are still working in and around California state government. So happy to share that model we have and a career guide for those of you with scientific backgrounds.
Wonderful, inspiring role model examples here. I'm just looking. So I think in the order, I think you were next, yeah? And then we've got a couple here and here as well, yeah.
It's very short. I'm working in vitro models on skeletal disease, and we are working in vitro in silico in vivo loop. So now we are talking about geopolitical shifts, and we have a lot of animal-free research movements across the world, specifically in Europe, also in US. I was wondering how you position then the clinical research and then reaching out to patients with this data.
Who wants to take a stab at this one?
I've been disciplined, so I was pulling back a bit. Yeah, we have had a number of this. I will try to be fast. We have had a number of discussions about the topic. I would say it's not straightforward. Definitely, these models need to be leveraged more. At the same time, these animal testings precede human testings, and you want to minimize the risk that you take with this human testing. So I think it's good evolution. Also, a lot of intention, for example, of diminish the utilization non-human primates, for example, in these preclinical trials, but work in progress.
Yeah. Okay. Gentleman here with the beige jacket and glasses.
Thank you, great panel. I'm Eric Vermetten from the Netherlands. I'm a psychiatrist, Leiden University Medical Center. And yesterday I spoke with my colleague Dimitris Brapantes and Roy Solomon on psychedelics. We had a packed symposium. And I'm just wondering, how resilient do you think that pharma is into, let's say, repurposing or reintroduction of an array of molecules, an array of compounds? And I'd like to hear also Hendrik Streeck, because what we see is a relative inflexibility of the regulatory systems in doing the research. Philanthropy drives it. There's not a lot of governments that are actually supporting. And there's a great need in mental health for novel therapies, specifically in the geopolitical situation that we're all in. So I'd just like to hear your comments on where the roadmap, or maybe the EMA is playing with this regulatory sandbox model that creates maybe some flexibility or so. I'd like to hear your opinion how to move forward.
Just before you, Dr. Vermetten's being very modest. He is actually one of the world leaders in psychedelic research. So
great.
There you go.
Very good.
Just to let you know.
Thank you, Alice.
Well, first of all, I think that we realized that we have a problem in our flexibility for clinical research, and we have to make changes there. We have too few clinical studies. It's too complicated to test in Germany substances. Myself, when I was 2 years ago, I wanted to start a clinical study on HIV cure, and I had funding, and at one point the funder said, this is just taking too long. We cannot do this. We are moving to a different country. We realize this, we want to make the changes. I can't tell you now how the changes are going to look like. I'm following actually the psychedelic research a little bit, just for example, for depression, right? And the clinical trials on there. What we have in this field, unfortunately, is sometimes the lack of good randomized clinical trials, and with some not psychedelic substances, but other substances, for example, diamorphin as a substitute, oral diamorphin, which is not licensed in Germany, and we need here also flexibility that we are able to look in other countries and see what have they done and how did it work in the field, in the practice, and accept this as a way of licensure also in Germany. This is something that the BfArM is doing in Germany, but these are ways that we are trying to explore right now, that maybe we have less strict rules by applying rules from other countries here in Germany as well.
Thank you so much. Fascinating discussions, and I'm sure there's a break soon and you can all reconvene and pick up on these discussions. I'm really sorry, but I need to stop now. I've been getting these signs. And I do have this final question to all of you, so if you can just give 1 or 2 words. So what walls need to break down in order to increase resilience in the pharma market amid these geopolitical shifts, so we can bring breakthrough medicines to the market as quickly as possible? Julian.
Cross-sector partnerships.
Cross-sector partnerships.
No, okay.
Cross-sector partnerships. Bureaucracy.
Yeah, and I think Hendrik brought this up. We need to accept research from other countries. We don't always have to do it in our own.
Good.
Thank you so much. It's been a really fascinating discussion. Thank you for tuning in.
Transnational partnership, yeah. Well done.
Okay. Key takeaway: cross-section partnerships. Yeah. So.